always a great pleasure, obviously, to be here, and I have to be careful. Slightly claustrophobic, I have to say, but okay, I'll do my best not to collide with the ceiling. It's a pleasure to be here.
Should we move the podium?
It's okay, it's okay. Oh God, it's a bit scary. So it's a pleasure to be here. And I'm going to talk, as Louis said quite rightly, about time crystal phases, fluctuations, and quantum correlations in spin boson systems. So a little bit of everything. And there will be a lot of connection points, I hope, to, well, the talks we have been witnessing this morning and also talks later, thank you very much, in the workshop. Just for those of you who don't relate to Tübingen at all, well, at least you have to understand where Germany is, yeah? Then you are in the game. So, so Tübingen is in the south, so the blue thing is Germany, Tübingen is in the south, so it's very picturesque. So it's like an old medieval town from the picture books, let's say. It's very nice, and I'm happy about being there, obviously, but I'm even happier to collaborate with a great bunch of people. So the stuff I'm going to talk about today will have been produced by Albert, Federico, Marcel, Robert, and Bea. And let's just jump straight in. So very briefly, I will talk about open quantum systems at the beginning, about spin boson model, so why this connection, then quantum master equation, and how this derives under certain circumstances from spin boson models. I will talk about feedback control. It's actually not necessary, the feedback, but it's actually fun to think about it, and you will see that one can use it to shift around phases and phase transitions in these quantum optical systems. It's quite neat. Then I will talk about waveguide quantum optics, because this is the setup parts of the talk are based on, and which is also the scenario, the platform that gives rise to the long-range interaction, which kind of inherits the title to this workshop. I talk about coherent interactions and dissipation, well, collective observables, and in the thermodynamic limit, how they, so to say, give rise to a mean field description of the system. Then we'll talk about dynamical phases, phase diagram, spin squeezing, which you get for free, which is quite nice. And then later, let's see, yeah, so you see there's no outlook yet. I will talk about other systems doing this interesting stuff in cavities and also in free space. So let's see how far we get. So just why spin boson model? Well, I would say one can argue that spin boson models are at the heart of almost everything. And for sure, our beloved quantum optics and atomic physics is captured to a large extent by spin boson models, where, well, spins are typically modeled by two-level atoms, or are representations of two-level atoms. The Hamiltonian is given by this expression here, where it's just describing the energy difference between those two levels under considerations. And then you have bosons, and one prominent, let's say, manifestation of bosons is the electromagnetic field, in which we typically immerse our atoms, and this electromagnetic field is, of course, described by such a Hamiltonian here, where A and A dagger are the annihilation and creation operators of, well, photon excitations, as you wish. And then you can look at the interactions, and then at the most basic level, we have dipole coupling. So the atomic dipole, so the transition dipole element, is coupled to the electric field at the position of the atom. And then you, of course, can write this down in this fancy operator language, where you see that in the end, everything is determined by this coupling constant, which tells you how strongly these raising and lowering operators related to electric magnetic field couple to the atomic dipole, represented by these Pauli raising and lowering operators. Okay, so this is why spin boson models are at the heart of everything. But of course, we will do some simplifying steps. But before we go into this, just some basic truths which will, so to say, guide us through the talk. So, well, interaction between atoms and light mediates dipole-dipole interactions. Tillman showed this very nicely in a slightly different representation. But at the end, this expression for this electric field that you showed is exactly coming out also of this formalism. Also, this funny modulation as a function of the Q times R that you have seen there. So the point is also that interactions with the electric that are caused by the electromagnetic field are not only coherent, so they are also dissipative. One prominent dissipative effect is, of course, spontaneous emission. So we know that when we have a two-level atom, or any atom, yeah, immersed in the electromagnetic field and prepared in an excited state, it will decay to the ground state. And this, of course, is a dissipative effect, which you also have to include if you want to look at the evolution of these systems over long times. And well, then the third truth, and this is probably the most interesting one, also for the purpose of this talk, and also Tilman, I'm very grateful that you dropped all these ideas already in this talk, depending on the mode structure of this bosonic field, yeah, whether, for instance, you put the atoms close to a surface, or inside a waveguide, or near a waveguide, or inside a cavity, the structure of these interactions, and for that matter also the structure of the dissipation, will change, yeah, and is strongly affected by how these modes are shaped that predominantly couple to the dipolar transitions within the atoms. Okay, so then there's a lot of math to be done in order to simplify the problem, and let's say under reasonable assumptions, what you end up with for this type of quantum optical system is a so-called master equation, Lindblad master equation, which many of you have most certainly seen already, describes the evolution of the density matrix of the atomic ensemble, and this is governed by a coherent evolution, yeah, mediated by a quantum Hamiltonian H, and some dissipator which is composed of these so-called jump operators Lj. Just to give a simple, so to say, picture of this in case of one two-level atom immersed in the radiation field. So we have and laser-driven. So we have here a Hamiltonian that describes coherent laser excitation of this atom in resonance. It's just the Rabi frequency times the sigma x operator, and then you have this dissipative effects which are modeled by this, or described by this jump operator, which goes here as the square root of the emission rate, kappa, and well, the sigma minus operator, that when you let it act on the excited state of the atom will demote it to the ground state. I think we have seen this in some or other manifestations. Good. Okay, so now this is our, let's say, open system that is described by this master equation. So think, for instance, in this particularly simple case that I showed you before, of the system as being an atom, two-level atom, and it depends on certain parameters, for instance, like the Rabi frequency, and this atom is immersed in the bath in this radiation field. This we have integrated out, yeah, so in principle we can live without taking an interest in it, but what we can, of course, also exploit is that this effective evolution of the system under the master equation is obviously caused by the fact that there is exchange of excitations or particles between the system and the bath. This is the reason for which the system doesn't undergo a closed Schrödinger equation evolution, but undergoes an evolution that is described by a quantum master equation. And what we can, of course, do now is we can look at what is happening in the bath. Yeah, well, let's say in a less abstract way, and relating to this example with the atom emitting photons, we can look at photons that are being emitted by an atom, and we can detect them. And based on the detection, we can now do something to the atom again. Yeah? For instance, change the intensity of the laser, apply quick pulses. This would be all manifestations of a feedback scheme. Yeah? And now the question is, how can we use this kind of feedback at the level of, let's say, quantum optics, quantum many-body physics in the quantum optical domain to do something interesting, yeah? And to, for instance, steer such a system, which is for sure then not a single atom, but a collection of atoms, into a stationary state that is in some sense interesting. Yeah? So this is the kind of story that I want to convey. So and first what we have to do is to think a little bit about feedback and okay, what is possible, and at least from the theoretical side, can be done in order to describe it. I mean, this is, of course, all, or to a large extent, already discussed in the literature here. This is a very nice book, Wiseman and Wilburn, about this quantum measurement and control. But it's also nice to just to think about for 30 seconds here of what this kind of inclusion of feedback entails. So, for instance, we can, for the simplest case, which we will not use actually in this talk, we consider photon counting. But this is something conceptually simple. Yeah? Whenever there's a photon arriving at your detector, and from a theoretician's perspective, this detector is 100% efficient. So every time a photon is emitted, I actually register a click. So what I can do is I can then immediately apply a pulse, a laser pulse, to the atom, And this I could, for instance, express technically through such a term. So remember this master equation, we had the so-called quantum jump term. I forgot to mention this explicitly, but for many of you have seen this, I think. So you see this is the process that happens. This is kind of an operation on the density matrix of the state that makes the state of the atom collapse. So this jump operator acts from the left and from the right. And what we just do with the feedback is that after this collapse, we apply, for instance, a unitary rotation here, so a quick laser pulse of area G to the atom in order to change its state. So this would be a feedback scheme where you immediately change the state of the atom after having registered a photon in your detector. So I think conceptually this is quite easy, and yeah, I think we can all agree that this is actually doable, so to say, at the theoretical level without great effort. So then it becomes a bit more difficult, or involved when you change the detection scheme. For instance, this photons, you cannot only detect them, so to say, in terms of intensity, but you can also detect the electric field, so-called quadrature, by coming up with some scheme that requires the imposition of another external reference field. But okay, those are details, but what matters is that what you register then is the electric field in the detector at time t. And this is a noisy signal. So this is a fluctuating quantity, well, with some noise around an average. But okay, this is, so to say, a theorist's impression of an amplitude of an electric field that you would detect. And now what you can do is you can now change also the laser, the Rabi frequency, the laser strength, as a function of this so-called photocurrent that you register via this homodyne detection scheme. And for instance, you can say, well, here's my photocurrent, and then there are some numbers to get the units right. Here's the rate, and here's the coupling strength. And you can ask what is happening to the system. So, and again, if you look at Wiseman and Wilburn, they tell you exactly what to do. So the photocurrent can be calculated in this way. So it's kind of an expectation value that you calculate for system observable. This is just a sigma x plus some noise. This is exactly what we see. And if you hack everything in into this formalism, you find that in the presence of this feedback protocol where you modulate the laser in a way that is proportional to the current that you are detecting, you have to not only modify this quantum jump term, but you have to also modify the Hamiltonian and the jump operators. So this is just a prescription that you end up with. Okay, details. Okay, keep that in mind. So this is still in Lindblad form. This is the simplest thing you can do, let's say. There are lots of approximations in this. Please, let's not talk about this. So, but conceptually, this is what is happening. So, okay, please keep this in mind for a moment. Feedback allows us still to use this Lindblad formalism to describe the open system dynamics. Only the feedback changes the Hamiltonian and the jump operators as a function of the feedback strength, so to say. So the system where I want to implement this is depicted here. So it's a chain of atoms that is positioned near a nanofiber or a waveguide structure. And this is exactly linking to what I said before. This is a means to shape the modes of the electromagnetic field so that not everything is just, so to say, described by, quotes, boring dipole-dipole interaction. Well, of course, dipole-dipole interaction is also present here, but here it does not decay as a function of the distance. Here it's mediated by modes that are extended over the entire system, and you essentially end up with an all-to-all interaction, which is kind of the extreme case of long-rangedness that we want to study and discuss in this workshop. All right, so let's talk a bit about the dynamics. We can also describe it to a good degree of approximation within this Lindblad formalism. Just want to talk you through the individual components here of this master equation. So you have a laser that excites your atoms from the side, and well, you have the laser detuning and you have the laser Rabi frequency. This is just a generalization of what I showed before of the Hamiltonian to the many-body case. And then I have this interaction, which is here taking place between the atoms, and it has this particular form, very reminiscent of what Tillman showed. So you have this flip-flop. One atom can so to say, de-excite, and another atom can excite when it absorbs the photon that was emitted by the atom that was de-excited. But here's not, so to say, a modulation in front that goes with 1 over r cubed. It's just flat, essentially. So there's a constant, and then there's this phase factor here. Yeah? And this is just due to the fact that the mechanism with which the atoms interact in this waveguide is through photons that are actually propagating in its waveguide. So the field strength, let's say, of this photon is everywhere the same. So this is why we don't have a modulation. The only thing that is making this whole interaction distance dependent is basically the phase that you get while propagating through it. Yeah? So these are these e to the k. My pointer just died. No. These are these phases here that depend on the interatomic distance. So, and then, so this is the interaction. And what you also have is you have emission. That's what I said. Decoupling to the electromagnetic field doesn't only give you, so to say, these interaction effects, but you can also have decoherence. And here you also have dissipation, but also the dissipation is special. So you can calculate it or model it with jump operators that are collective. So this is just not a sigma minus for atom 1 and a sigma minus for atom 2 and so on and so forth. These jump operators, yeah, and there's one for a left propagating mode and one for the right propagating mode, are collective in the sense that they are just a sum of single atom jump operators with prefactors that again come about due to the fact that we pick up this phase due to the propagation of the photon in the waveguide. Yes, there are two questions. Yeah, please.
Should I think about n atoms or like 6 or like how many?
N equals 6 is also good. No, but we will go to the thermodynamic limit. But again, I mean, take it with a grain of salt. So I mean, obviously, when you build it in the lab, well, I'm saying obviously. So without the obviously, when you build it in the lab, you have a finite number of atoms. Later on, when we do some theory gymnastics, we let n go to infinity.
But realistically, how large is it? How many atoms can you couple in this?
There's an experimentalist in the room that can answer this. I think, I mean, most would say familiar with Rauschenbeutel experiments, and that's, well, I think, on the order of 10, 20, 50, yeah, something like this. Well, it depends how well you can position those. I mean, I'm really talking about the lattice, and I'm thinking these lattice experiments are not done with thousands, but not too small, let's say, larger than 6. So, and then there's also this emission into unguided modes, which we will not talk about. We'll come back to this later, which is, of course, a problem, but nothing that, let's say, is unsurmountable.
Sorry, what sense K? I think you might have already said this. But
say again, what?
What fixes K? It's a waveguide, right? So K is a continuum of modes.
This, okay, good question. So this is the K that corresponds to the wavelength 2 pi over lambda of the atomic transition. There's actually a modification due to the index of refraction within the waveguides, but let's say to 0th order approximation, it's just a...
About resonant interaction.
Yes, yes, indeed, yeah. No, of course, you have to, shouldn't say, of course, again, you have to build the system such that you are compatible with the atomic transition. Yeah, also these photons that are scattered from the atom, they have to be the ones that are guided by the waveguide. Yeah.
There's also guys that are not exactly in resonance, right? There's a sum over modes that sort of peaked at the resonance. So are you treating that, or are you just approximating?
No, I think you can really make these waveguides such that you have 2 modes. I mean, in the ideal case, yeah, that are guided, and the rest are free. Yeah, they are modified also by the presence of the waveguide, but they are not the ones that are actually guided. I mean, they are nano fibers, for instance, in the case of the Rauschenbeutel experiments. Yeah. Okay, so let's simplify this, and I really have to be conscious of time. So now some drastic simplifications. Yeah. So this was just the motivation, telling you that if you wanted it to be more complicated, you can have all the complications there are. Yeah. But now we are doing some drastic simplifications. So we say first we neglect, as I said before, emission into unguided modes. And then we say that the atoms are positioned next to the waveguide in a way that they are commensurate, that the spacings is commensurate with the wavelength corresponding to the emitted light. So then there are lots of simplifications. So the interaction term goes away, You would think, okay, this is bad. No, it's not. It's actually good. Yeah. So, and then the only thing that remains is essentially just a bunch of two-level atoms that you are resonantly driving with a laser. We also put everything on resonance, so there's no detuning. So, and now it's important what we do is we now implement a measurement, yeah, on the right-hand side, on the right output of this waveguide, where we do this homodynamic detection and then change the laser Rabi frequency proportional to the output signal that we detect here, yeah, and crunch everything through the formalism. And what we then get is a master equation that depends only on collective spin variables. So it's always the sum over sigma matrices that enters the description. All the operators are composed of sums of sigma matrices. So not, let's say, the atoms lose, so to say, their individual identity and everything, so to say, closed expressions in a closed expression formulated in terms of this, yeah, angular momentum, big spin angular momentum variables. So this is the equation that you get, yeah, when you crunch this through the formalism. And what you find here is that you get a feedback generated term in the Hamiltonian, and you get some modified jump operator here with jump operators that now depend on this feedback strength G. Yeah, and you see, this is the jump operator that is actually related to the detection of the photon here on the right output port. If you look at this one here, which refers to the detection of the photon on the left output port, it's actually not modified. It's just a sigma minus operator here if you add these two things together. Okay, so no feedback condition on photons emitted into the left propagating channel. And now we go to the thermodynamic limit because, well, now we want to have things simple. So in order to do this, we introduce so-called magnetization operators, and these are operators which are given by the angular momentum operators divided by n. And in the limit in which n is large, these operators, these magnetization operators, become actually classical variables in the sense that their commutator, again, in some well-defined sense, on a certain set of states, yeah, so take this with a grain of salt, their commutator becomes 0. So, and then you can prove, yeah, that actually in the thermodynamic limit, you find that this evolution of the system is governed by a set of mean field equations. So there's a small caveat. Well, it's actually also not something that you find totally shocking when you have been working in this field for quite a while. You have to rescale the emission rate here, this gamma, so this is the photon emission rate into these guided modes, in a way that you divide it by n. So why is this? Only if you do this rescaling, you approach a well-defined thermodynamic limit. This has just to do by looking at how these terms in the master equation scale when n grows big, and you want to have something in the end that is intensive. And long story short, you only get this when you do the rescaling. This is, of course, important for experiments. I hope we get to this. I have to see. Yeah. So, but from the theorist's perspective, it's a completely accepted approach. But if you really want to do something in practice, you have to take this into consideration. And now you get these mean field equations, which I said are provably exact. And you can now look at the mean field phase diagram. Let's say it gets interesting at some point. I mean, I think so far we can agree there's maybe the entertainment value is limited. So mean field, many of us can do. Yeah, it's nice that one can prove that it's exact. But okay, so what we knew that before from numerical simulations that can be done very efficiently on this kind of systems because everything is governed by this macroscopic spin variable. But what we find, and this is maybe the first thing we start with now, is a mean field phase diagram that looks like this. And we have 3 phases. We have a stationary one here where this magnetization is 1/2. We have another stationary one when the magnetization is minus 1/2. And this is where I want to start, so to say, the discussion. So, and we move here to a feedback strength of 0.5 and look at the position in parameter space, which is represented by the square. And then we find very nicely that the system really, when we let it run, approaches a stationary state. And just to say as a visual corroboration of the fact that mean field becomes exact, ultimately here's the simulation for different system sizes, and you see in a credible way this converges to this infinite size limit here. So then you have a phase which has actually on average zero magnetization. I say on average because if you look at the thermodynamic limit, you find that you have actually persistent oscillations. This is the so-called time crystal. I mean, if you want to call it time crystal, I also don't care. Yeah, I mean, it's a nonlinear system that you can solve, and you find a regime where you have not a stationary state. This is not so much the point. It will become more interesting in a couple of minutes' time.
Like a limit cycle.
This is a limit cycle, exactly. It's not, so to say, you see, it's not monochromatic in some sense, so there are more higher frequencies there, but funny thing is that at this point you find that this is really a limit cycle which has only one frequency, namely the frequency of the Rabi frequency of the laser. So this is what you could control with the feedback.
And why that is dumping to your state?
Exactly. So this is, thank you very much for this question. This was not choreographed. So the damping is for, you get your $10 later outside. What happens there, these are finite size effects. Yeah? And you find that you get, I don't know whether I've seen, yeah, when you look at the, so to say, the spectral gap of the system in this oscillating phase, then you find it scales as 1 over n, the particle number. Yeah? And you decay, so to say, on a time scale that goes with 1 over the particle number. It's actually super interesting if you look at, I'm probably not getting to this, if you look at single trajectories. I mean, it's a bit like a laser. You can imagine this. I mean, it's not at a single frequency, but you can, imagine this is just the average value. So what you would observe, let's say if you were to, for instance, to look at the photons that are output by the system or the current, that photocurrent, you would see oscillations all the time. But the damping is happening due to the fact that you have phase slips every so often. Yeah? At the end, yeah, when you look at the average, you have to sum over everything, and there's a certain coherence time, right? And beyond the coherence time, you see that you go to, let's say, a stationary state, which is then unraveled as a, let's say, superposition or mixture, maybe better, of many oscillating solutions. Yeah? This is how you can rationalize this stationarity. But at the level of individual realizations, you would see that you always have these oscillations. And then you can analyze these phases, and you find, okay, in a stationary phase, you're somehow you're gapped, you are independent of particle number, then there's a critical point between the stationary phase and this limit cycle or time crystal phase. And at the critical point, you have another scaling as 1 over square root of n. This has been known. I mean, I would not even say 2018, so since the 80s, I would say, yeah, if you look at the literature. Now let's make this a bit more interesting. So what about quantumness? Yeah, so, okay, because there's always this criticism, and to some extent I share it also, that there's some bogus, yeah, this time crystals. Yeah, maybe we hear about this also. In the end, it's just mean field, nonlinear dynamics, so what, who cares? Yeah? But the nice thing is that you can now go beyond this. You can really ask, okay, what properties do the fluctuations of this state have? So what can I say beyond mean field? And this is actually very nicely doable in the framework of so-called fluctuation variables that you can introduce, which are now, so to say, the next thing you attach to these magnetization operators. So they allow you to go further in the description of the system in the sense that you can now capture fluctuations. And you see they're quite intuitive here. You take the component of your angular momentum operator, subtract the average value, and divide by square root of n, which turns out to be the proper scaling for describing this. And then you can write down with this the so-called covariance matrix. And you can look at commutation relations. It will just get interesting in a second. And you see these commutation relations between these fluctuation variables. Okay, there's something. Yeah? There's some matrix here, S alpha beta, which parameterizes the commutators among these different fluctuation variables. And you see this matrix S that here describes, so to say, or parameterizes this commutator, depends on these mean field solutions, the mean field magnetizations. So what you can do now, it's a bit like Holstein-Primakov, yeah, but I would say a little bit more better controlled. What you can do now is you can go to a new basis where this matrix here becomes diagonal. Yeah? And this is a basis where you move, co-moving with the mean field solution. Yeah? That, okay, if you're in a stationary state, you don't have to move because you're stationary, but when you're oscillating, in this limit cycle case, you have to move your frame of reference. so that this mean field is always pointing in that direction, and then you have fluctuations in the transverse directions. Yeah. And in this rotated frame, what you can do is you can actually see that these operators, these fluctuation variables, they can be interpreted as momentum and position. Yeah? Or as bosons. You can also do this. Yeah? And you can rescale them in a way that you get these canonical fluctuation, canonical commutation relations. And now you are immediately in position to ask about the quantum properties of the state. Yeah? For instance, squeezing. Yeah, in this XP plane. No, I mean, okay, for states we can, well, let's say this is a prototypical squeeze state. You see, there's an elliptic. You have squashed or more minimal uncertainty in one direction than in the other direction, and you can ask. And these states are important, for instance, for quantum enhanced sensing, because you can imagine that when you measure now in this right direction, the projection noise is strongly reduced in this direction compared to the other. This is why these states are useful. And now you can go back at this phase diagram, but you do not calculate the order parameter, so the magnetization, but you calculate the squeezing parameter as a function of the feedback strength and the laser driving strength. So spin squeezing is always present when the squeezing parameter, which basically is the ratio of these principal axes, is below 1. And let's now look at what happens, yeah, where this happens. And you see now, if you move along the same track here for the same feedback strength, yeah, from the bottom to the top, you find that in this stationary phase, which we here call squeezed phase, you see that the squeezing parameter goes lower and lower. The closer you get to the transition, the closer you get to the transition, the more prominent also finite size effects become. But if you happen to go to the thermodynamic limit, you see that in the extreme case, when you approach this phase transition from below, from the stationary phase, the squeezing becomes infinitely good. Yeah, it approaches 0. So you get a squeezed state, and you can check this also numerically. Yeah, so you really get as a stationary state, a pure state, which in the thermodynamic limit happens to be a perfect squeeze state with arbitrarily good squeezing the closer you are to the phase transition. So basically at the press of a button is maybe too much to say, you get this state which in principle would allow you for implementing quantum enhanced sensing schemes. So there are some papers about this on the archive by Matteo Paris and Diego Porras, which look at this phenomenon in this model. I'm still a bit skeptical, but I'll come to this in a second. I don't know, Louis, you have to tell me.
We have in principle 4 minutes, but since there were questions,
okay. Okay, but I will pick this up later, but I think, okay, what you can already save on the hard disk is, okay, squeeze state for free. And the squeezing gets better the closer you are at the transition. So now, what you can also do, and this is why I like this theoretical approach so much, is you can now really look at what is actually the dynamics under which these fluctuations evolve. We have already identified them as some kind of, well, bosonic operators or X and P operators in this plane, but we can ask also, how do they evolve in time? So what equation of motion is governing their dynamics? And this is just, so to say, a fun fact. You find again that this equation of motion for these fluctuations, so in this plane, perpendicular to the big vector that, so to say, determines the order parameter, that these fluctuations also evolve according to a dissipative dynamic. So this really looks like the dissipator of the master equation. But these jump operators here, they're actually time dependent. And they depend on the instantaneous values of the mean field solution, which is also kind of nice. Yeah? So it's a master equation, but it would not be, let's say, considered a Markovian master equation because there's this explicit time dependence of the operators and rates. And this allows you now also to study the evolution of the density of the elements of the covariance matrix just very briefly. Yeah? You see here again clearly these two phases. Yeah? Time evolves, and when it evolves in the stationary state, nothing is really happening to these two directions of the covariance matrix, whereas in the time crystal phase you see these growing covariance entries, which basically tell you that fluctuations grow without bound in the time crystal, which also implies that it's not super useful for some quantum enhanced sensing protocols. And you also see this here when you now at the critical point look at the entries of this covariance matrix. So one entry shoots up with t, one entry goes down as 1 over t, and this is the origin of this ellipse that forms. Yeah? One principal axis increases, one principal axis decreases, and this is why you get then this perfectly squeezed state with squeezing parameter 0. So you can also see this in other systems. Yeah? Obviously, this maps 1-to-1 at the level of the theory, also at atoms confined in cavities, yeah? Where you have here an external laser coming from the side, you have these two-level atoms, and you have here just one cavity mode. And you can also, in this case, introduce loss, yeah, which we need in order to get a stationary state through, for instance, loss of cavity photons, yeah, for just non-perfect mirrors. This again we have seen, and we will see in the course of this workshop, can be formulated in terms of a master equation here, where we have the Hamiltonian that describes the atoms in the cavity also by this macroscopic spin observables and also the photons of the cavity. And you see here this usual coupling, this Davis-Cummings model, with also a coupling that is parameterized as this 1 over square root of n to so to say, make the thermodynamics right in the sense that everything has to be intensive. Sorry. And then you have here dissipation on the photons, due to this loss channel. This can be mapped, and I don't want to lose too many words about this, by means of adiabatic elimination also onto this previous model that I discussed, this model that gives this boundary time crystal, namely in the case in which this cavity loss is large. Then you can adiabatically eliminate parts of the dynamics, the photons in the cavity, and get just a model for the spins, which looks exactly modulo the feedback generated terms, which are not super important, as I said at the very beginning, like the equation that I had before. Okay, but still, one can now ask what happens if I look at this system in the cavity, but not in a regime where I adiabatically eliminate the cavity photons because I have the strong damping, but in a regime where I have somehow, damping rate that is similar to the interaction rate or even smaller. So then you can plot this phase diagram here, so which parameterizes the spin-boson coupling. Kappa is the damping rate. So for large kappa, we can do this adiabatic elimination, and then we see very nicely as a function of this laser driving strength, we also have this phase transition here. For instance, along this red line, you see here we have a stationary phase, and then if we move to the right, we cross a phase transition, and then we are in the time crystal phase. And everything below that is then also in the regime where we can do this adiabatic elimination. We just change the parameter values quantitatively, but qualitatively everything stays the same. Interesting it becomes when the cavity, or when the spin-boson coupling strength becomes comparable to the loss. Then you see suddenly there's something opening here. And you see here some kind of wedge that opens up. Here to the left of the wedge, we have a stationary phase. So the yellow signal is just time integrated to even out the bumps, so which is more important in the time crystal phase. You see in the time crystal phase, you have these oscillations. And when you do the time integration, you just go to some stationary state. But what you find in between, this is actually interesting, is you find now that in principle, when the spin-boson coupling and the decoherence rate or photon emission rate are comparable, you find a regime of bistability, or phase coexistence, you could also call it. And I think, you can either look at this plot or you look at this plot. You see very nicely this phase coexistence manifests in the fact that depending on where you start initially, you either end up in a stationary phase. So this is, so to say, this is this red curve here. So let's say here's the initial condition, and then you run towards the stationary fixed point, or if you happen to be in the basin of the attraction of this limit cycle, you will run to it and just perform oscillations for eternity. So this is also something that one can probe. So really this kind of ergodicity breaking manifest in this bistable or phase coexistence regime. And then this is almost my last slide. And then beyond the cavities, there has been a nice work by Antoine Brevet. This also links very much to what Tillman said. Maybe this is also something you can do, yeah? Who look at very tightly confined atomic ensembles in free space. Yeah, you see, I mean, you look at ensembles that have transverse width or below a wavelength and just a length on the order of 10 wavelengths. There also you have this, well, weird, let's say, coupling between the atoms and the radiation field, where the atoms lose their individual identity but couple to the radiation, to the electromagnetic field as a collective. And this you can also model with this kind of boundary time crystal master equation that I showed you before, and that you can also get in this atom cavity setting that I showed you before. So this is actually super nice, and they have done some measurements, yeah, which everyone wants to believe maybe show this transition into, we would call it limit cycle phase. They call it differently. That's fine, yeah, or time crystal. The problem so far, and I think this is also really something that is generally a problem when you want to transfer these ideas from theory to experiment, is that the detection rate of photons is very small, and also the current is very small. So there are very few photons only per time recorded or even emitted by an ensemble, because the driving is also weak. So I don't want to overwhelm you with this, yeah, but so the point is now, and we were asking ourselves, what if you could now operate the system really in a regime where you have relatively large photon flux? So is it actually possible, and this links to what I said a couple of minutes back, to now see these different phases in the trajectories, yeah, in the photo output, yeah, either in the photon count or in the photocurrent that I can detect here in principle at these detectors. And again, as I said, so this model has a phase transition between a stationary phase and this time crystal phase, and now you can have different observables. Yeah? So we are just scanning through here again. Here's the stationary phase, here's the time crystal phase, here's the critical point. And then the first line is, so to say, theorist's impression. So a theoretician likes to calculate expectation values of magnetizations. So this is an observable relating to the atoms in here. So this is not immediately accessible, right? Of course, you can measure it in principle, but let's say for solving the mass, for theory, it's not difficult to do this. And you see very nicely that you indeed get somehow either a stationary phase or a time crystal phase. And at the critical point, you also find something very funny, which we didn't anticipate. The system is basically stationary for a long time and then has a huge spike. Stationary for a long time, and then there's a huge spike. And you can also make meaning of this, yeah. So by looking at the mean field model plus fluctuations, and it's really funny, yeah, that also these spikes are distributed, for instance, according to a power law. Yeah? It's a bit like earthquakes. It's the same. Yeah? So it's a critical phenomenon. You would also expect this, but this for us was quite curious and has not been seen so far, I think.
So this is without feedback?
This is without feedback, but this is, so to say, what you would. I mean, it's in the same vein, because this, not this, but in principle, the photon count or the homodyne current you could observe with if you wanted to implement feedback. And you see the same structures, I make this short, reflected in the photon count and also the homodyne current here. So at the critical point, these spikes, yeah, less pronounced, but you can also filter the signal and you see it a bit better. But here in the homodyne current, you see this very nicely. Yeah, you have these spikes and a long time nothing, then spike again. And in the time crystal phase, you see these oscillations. If you were to Fourier transform the signal, it would be clear that there is a peak on the, let's say, expected time crystal frequency. Okay, summary and outlook. So first part, I showed you that we can control this long-range interacting system with feedback and get, so to say, in principle, a squeeze gate for free with a controllable squeezing parameter. Can now ask, okay, how can one use this quantum matter on demand somehow in such an integrated system? There's this quantum enhanced sensing ideas, yeah, by Paris and Porras. There's this question, I should have flipped the order here. There's the question of this 1/n scaling, which I mentioned, which they include and get then quantum enhancement, yeah, in some way, because you want to have this signal to noise scale in a certain way, and so to say, quantum Fisher information to scale in a certain way. it's a bit cheating, yeah, if you start with the equation of motion where the n is already implemented in the start. Yeah? So this is something to be revisited. Then you can ask, just for instance, Tillmann Esslinger was asking this in his experiments, and Tobias Donner about creation of non-Gaussian states. So far, what we found are Gaussian states. And then also the role of the emission into unguided modes. This is something you have to face eventually. But there you can also, of course, not expect that at stationarity you will get these perfect phases that I showed you, but there will be a metastable, a transient regime over which you will observe these effects. And then for very long times, these time crystal phase will also not survive. But again, might be also a bit academic because in practice also experiments are conducted over finite times. Okay, thank you very much for your patience.
Okay, I think we are